on the context of energy. So we're going to answer a few questions about energy. Again, the most important things when talking about energy is the idea of the law of conservation of energy, right? Energy is neither created nor destroyed. The energy in the system will stay the same unless acted upon by an unbalanced force, right? So unless there's something from the outside acting on the system, the amount of energy in the system will stay the same, right? So what just happens in the system is that energy is changed into other forms of energy, right? From potential to kinetic and vice versa. Uh, so what we have here, so this is the first question that we have today, deals with that, right? Deals with the idea of conservation of energy. So here we have a box of mass m is held at the top of a frictionless incline. When the box is released, it slides down the incline off the table at a horizontal angle and falls to the floor, as shown in the image below. The X marks the spot where the box lands on the floor. So we're going to have here is going to have a mass like m, right? So we're going to have a mass m sliding down, and then it's going to fly off horizontally and eventually landing on x. Okay, so that's the basics of this context, or the basics of this problem, and the slide itself has no friction, right? So friction is negligible, friction is meaningless in this problem, right? So part A is asking, what is the total energy of the box at the top of the inclined plane before it is released? So I'm looking for potential energy of the, or the total energy of the system. So the total energy of the system, right, before it's released, right? So before it's released, that means it has zero velocity. If it has zero velocity, that means it doesn't have kinetic energy, right? And since it has height, we know it has potential energy. So we know at the beginning, all of the total energy of the system is just potential energy, right? So in the beginning, the total energy of the system is just the potential energy of the system. And you know potential energy, right, is mgh, right? Mgh, right? That's the equation for potential energy. But the problem here, right, we just don't have one height, we have two heights. We have h1, which is this, and we have h2, which is this, right? So all we have to do, right, is we know that the height of the system, or how high the mass is mg h1 plus h2, right? It's the height of these two heights together, right? That's the height of the mass, okay? So in relative to the ground, it's going to have a height of h1 plus h2. So that's going to be our total energy, right? So in the beginning, all has potential energy, and this is our total energy of the system. This is how much the energy of the system has, or how much energy the system has throughout this entire thing, right? But in the beginning, all it is potential energy. Okay, so that's part A. Part A is the total energy of this box. It is going to be, since we're not given numbers, we're given variables, we just have this as our answer. So the total energy is equal to mass times gravity times the two heights together. Okay, that's the total energy of the system. So now they're asking for, what is the horizontal velocity of the box after it leaves the table edge and falls to the floor? Okay, so what is the velocity of the box as soon as it leaves the table edge? So what is the velocity, right, of the mass as it leaves the desk, right? So we know what we're told here is that the mass, right, is going to slide down the incline, okay? And it's going to slide down at a horizontal angle, right? So it's going to slide down horizontally as soon as it leaves the table, right? So as soon as it leaves the table, it's going to have a horizontal velocity, okay? So we're going to find the horizontal velocity at that point, okay? And we're going to do it, since we're not given numbers, we have to use variables, right? So again, all of these problems, all with energy, it just deals with the concept of conservation of energy. So all of the energy that we have in the system comes from this, right? Comes from the potential energy we have in the beginning. So let's look at the energy of that system. Let's look at, this is for part B. Let's look at the total energy, or what kind of energy it has as it leaves the table. Right? So we know it has velocity. So if it has velocity, we know it has kinetic energy. So the total energy, right, is going to have kinetic energy. Yeah? And we know that it has height, right? If it has height, we know it has potential energy. So the total energy of the system right here, right, as soon as it leaves the table, is both kinetic and potential energy. Okay? So we know that kinetic energy is 1/2 mv squared, right? So m v squared. So this velocity right here, right, is going to be the velocity that we're looking for. What velocity does it have as soon as it leaves the table? So this is the velocity that we're looking for, right? This v in 1/2 mv squared. And we know potential energy when it leaves the table is mgh, but it's just the height of the table, right? It's not the height of the slide. It's just going to be the height of the table because, it already went lower. So it's going to be mg, right? And h, h. So that's going to be our total energy here. It's a mixture of kinetic and potential energy. And we know the total energy that we had in the beginning is this, right? We figured it out. The total energy that we have in the beginning is the potential energy of the system when it was at the very top, which is going to be mg h1 plus plus h2. Okay, since we know those are both total energies, we know, like, since energy is conserved, these two energies are equal, right? The potential energy when it was at the very top, and the total energy, the combination of kinetic and potential, while as soon as it leaves the table. So these two, we can set these two equations equal to each other, and then we have to look for velocity. So we look for this, right? Should be pretty simple. I guess to, like, simplify the problem, I can do this, right? I can distribute is equal to 1/2 mv squared plus mgh1. Okay, so I subtract mgh1, and you get mgh2 is equal to 1/2 mv squared, right? And then we just solve for v, so we do times 2, so 2 mgh2 is equal to mv squared. Then we divide the m, so 2gh2 is equal to v squared. Then we do the square root, and velocity is equal to the square root of 2gh2. That's the answer. Okay, so the horizontal velocity, the velocity of the system as soon as it leaves, is going to be 2. Okay, and just put horizontal velocity is going to be 2gh2, the square root of 2gh2. Okay, so that's going to be the horizontal velocity of the system or of the box as soon as it leaves the table. Okay, and again, as soon as it leaves the table, it has both potential and kinetic energy. So all of this potential energy at the beginning became a little bit kinetic and a little bit potential. So now let's look at part C. And then give myself a lot of space, so let's just do it off the corner here. So part C is use the conservation of energy arguments to find the vertical velocity of the box just before it strikes the ground. Okay, so we're not going to use kinematics because they tell us to use the conservation of energy. Okay, so we're going to use the concept of conservation of energy to find the velocity of the box as soon as it hits the ground, right? Or just before it hits the ground. So we know is that when it leaves, right? When something, when this box leaves the ground or leaves the table, it's going to have a it's going to have a horizontal velocity. And that horizontal velocity is what we found, the square root of 2gh2, right? But we know as soon as it leaves the table that it has a horizontal velocity, but it doesn't have a vertical velocity, right? It has a vertical velocity of 0, and then the vertical velocity will go up, right? The speed of the box vertically will go up, right, as it falls, because acceleration of gravity will increase that speed. Okay, that's what we know. Or that concept is what we know. So let's think about what's going to happen here, right? So we know, and this is very important, we know when it hits the floor, right? Since remember, like, we're gonna ignore air resistance, right? So with the object moving to the right, like, the horizontal velocity of the object is going to stay the same throughout, but the vertical velocity of the object is going to change as it goes down. Okay, so we know that this object, when it falls to the ground, will land at an angle. Okay, so the box will land at an angle, so that means it's going to have a horizontal velocity, and it's going to have a vertical velocity, right? So it's going to land as a vector, so we know it's going to have a vertical and a horizontal velocity. And since we know the horizontal velocity doesn't change because there's nothing acting on it horizontally, we know that if it's the horizontal velocity is 2gh2 as soon as it leaves the table, it's also going to have a horizontal velocity of 2g, or the square root of 2gh2, right before it strikes the ground, right? I don't know the vertical velocity, right? But that's what I'm looking for. So this problem is super easy. And again, like, we should I want you guys to think about this, right? Right before it hits the floor, what type of energy does it have? Okay, type in an answer. But right before it hits the floor, my question is, what type of energy is it going to have? Okay. So the type of energy it's going to have, and this is very, very important, is that like, hey, does it have a height? No. That means it doesn't have potential energy. Does it have motion? Yes. We know it's going to have a horizontal and a vertical velocity, so it has kinetic energy. And remember, right? So all of the energy in the system, as soon as it hits the floor, right before it hits the floor, it's just going to be kinetic energy because it no longer has height. Okay, so that means all of the energy that we had in the beginning, all of this total energy that we had here becomes kinetic energy. Okay, so we can solve for that, right? So we can solve for the velocity that it's going to have when all of the energy becomes kinetic energy. Okay, so I know that the total energy becomes just kinetic energy, right? So let's solve for it. So right here we have a total energy in the beginning. We have just potential energy, right before we released it, and all of that energy is mg h1 or parentheses h1 plus h2 close parentheses is equal to 1/2 mv squared, right? Because all of the energy becomes kinetic energy. Okay, and then now I can solve for velocity, right? This is super easy. Can easily solve for velocity, and I'm going to get 2 mg parentheses h1 plus h2 close parentheses is equal to mv squared. Then divide by m, I get 2g h1 plus h2 is equal to v squared. Then get the square root of 2g h1. Oops, sorry, I keep forgetting the parentheses. 2g parentheses h1 plus h2 close parentheses is equal to v. Yeah, so that's going to be the velocity right before it hits the ground. But remember, this velocity is going to be a slanted velocity, right? It's going to be a velocity at an angle. But we're not looking for the velocity at an angle. We're looking for the velocity, right? According to this, we're looking for the vertical velocity. Okay, so we have to find the vertical velocity of this problem, but that's super easy. So what we have here is we have, right, let me redraw what we're going to see here. Let me redraw the vectors of velocity as soon as it hits the floor. Right, we're going to have our actual velocity here, and we've solved for it to be 2g square root of 2g h1 plus h2. Right, that's going to be our velocity, our actual velocity. We know, right, our horizontal velocity is going to be square root of 2gh2, right? And we're looking for our vertical velocity, okay? And remember, guys, when we're working with vectors, this becomes like a triangle problem, right? This becomes a very, very simple triangle problem, right? Where our vector, right, our real velocity is going to be our hypotenuse, and then these two, the vertical and the horizontal, are going to be our adjacent sides, right? The adjacent sides of a right triangle. So if we have my hypotenuse, I have one of the adjacent sides, and I'm looking for the other side. Know that we would just utilize, right, trig quantity to solve for it, or right, even easier is all of you guys are familiar with Pythagorean theorem, right? Every single one of you is familiar with Pythagorean theorem, right? So we have like a, b, c, and a squared plus b squared is equal to c squared, right? All of us know that, and then we can just do it, right? So what we can do is we're looking for vertical velocity, okay? Plus the other side is square root of 2gh2 squared is equal to c squared, right? Which is our actual velocity. I'm going to put it at the bottom. Is the square root of 2gh1 plus h parentheses h2, right? And then we would square that. And you guys know squaring a square root canceled out the square root. So now we have v squared is equal to vv squared plus 2g H2 is equal to, I'm going to put it in the bottom, 2gh1 plus h2. Okay, so now we're just going to solve for the vertical velocity. So here we're going to have vertical velocity, and I'm going to extend it here. Vertical velocity is equal to 2gh1 plus, and this is parentheses, plus h2 minus 2gh2. Okay, and if I want to simplify it, I'm going to get, and by the way, this is v squared. V squared is equal to, again, I can just multiply it, right? So 2gh1 plus 2gh2 minus 2gh2. If you notice, we can cancel this, and we have v squared is equal to 2gh1, right? And then we just do square root, and we get vv, or the vertical velocity, to be the square root of 2gh1. Okay. Now we found the vertical velocity. Okay. So the vertical velocity here is square root of 2gh1. Okay. Again, pretty simple. You just have to understand, once we have like one, you have to understand conservation of energy. Two, you have to understand that like the ideas of vectors, right? If we have the actual vector and we have one of its components, what we can do to find the other component is trig, right? Or in this case, even easier, Pythagorean theorem. So part D. Part D is, what distance from the table edge will the box strike the ground? Okay. So what distance? So we're going to look for, again. So we're going to look for the horizontal distance between the table and X. Okay. So we're looking for that horizontal distance. Again, we have several equations to solve for it, right? To find that horizontal distance, we would have to use the horizontal velocity, right? And we have this equation. Velocity is equal to distance over time. We know horizontally there is there's no acceleration, right? The velocity horizontally will not change. So all we have to do is this. Okay? So we know the so horizontal velocity is equal to the distance over time. We found the horizontal velocity to be square root of 2gh2 is equal to distance over time. And then we would have to find time. The problem is, like, we don't know time, right? We don't know time, and we don't know d. So we would have to find, and they don't tell us like we can use time as a constant, or that we can use time as a variable. So we would have to solve for time with the variables given to us, and that's not too difficult. So remember, guys, what you should know here, the time for it to travel horizontally, the time for the box to travel from here to here horizontally is the same time it would take for the box to get to travel vertically from here to here, right? So the vertical time and the horizontal time will be exactly the same. So what I can do is like, hey, I can find the vertical time using kinematics, and then I can substitute that vertical time in the horizontal equation, and that would be it. Okay, so let's find, this would be for part D. So let's find the vertical time. So we know the vertical velocity, right? The initial vertical velocity. So I'm going to put VVI is equal to square root of 2gh1, right? And then what we know is acceleration due to gravity will be g, or in this case, like negative g, I guess. Yeah, it would be acceleration due to gravity would be, actually, let's put positive g instead. So just making down positive, just to make it easier for us. So we have the acceleration, and then we have the distance. We have the distance, the vertical distance it will travel is h1. Okay, so that means the change of x will be h1. And again, as long as we know three things for a kinematics problem, we know everything, right? And we're looking for time. Okay, so let's think of an equation that we can use. I'm going to use the second equation, right? That's going to be change of x is equal to VOT plus 1/2 a t squared. Okay, so I'm going to use the second kinematics equation. We have change of x as h1. We have the initial velocity as 2gh1 t, and then we have plus 1/2. We have acceleration as g, right, t squared. Okay, so we can do this, but I guess this might be a little bit more difficult, again, because we would have to like utilize quadratic formulas to solve for it. So instead, I guess we can use the third equation, and then we can use the first equation. Third equation is VF squared is equal to VO squared plus 2A change of X. Okay, I'm doing this to solve for VF, and then I'm going to utilize the first equation, which is this. Okay, so what I'm going to do is I'm going to utilize the third equation to find VF, and then I'm going to plug that in to the first equation to find T, right? Just makes things simpler for us. So I know VF squared, I know VO is the square root of, this is 2GH1, is the square root of 2GH1 squared plus 2A, which in this case would be acceleration due to gravity, 2G, and then change of X is H1. Okay. So I can solve for VF. VF is equal to, the square root of 2G, because this would cancel, right? 2GH1 plus 2G H1, right? And in that case, if once you do that, you get VF is equal to the square root of 4GH1. Okay, because you can add other like terms. So now we have the final velocity. I can plug it in here to find time. So I'm gonna have square root of 4GH1 is equal to VO, which is the square root of 2GH1 plus acceleration is G, and then time. Okay. So I'm just going to square root of 4GH1 minus 2GH1 is equal to GT. Okay, and then I'm just going to divide by G, right? So I'm going to have square root of 4GH1 minus 2GH1 over G is equal to the time. And then I can simplify this further, and I'm going to get 2GH1 over, or the square root of 2GH1 over G is equal to time. Okay, so that's going to be my equation for time. And then I can plug it into the to the horizontal part, right? And I know this is a pretty long problem, but I can probably do the horizontal part. Remember, horizontally, there was no distance over time. There was no change in acceleration. There was no change in velocity. So we're going to utilize this equation. VH is going to be the square root of 2GH2, right, from the problem we just did. And then now we have time. Okay, the time is the square root of 2GH1 over G, okay, is equal to distance. Okay, so now we're just going to have to solve for VO0 for the y-axis. You know what? Yes, it is. Oh my god. Alright, so I messed up with this whole thing. You're absolutely right. VO is 0 for the y-axis. Whoops, yeah. So I did mess up here. My bad. This problem's a lot easier than I had it out to be. Okay, so we can actually just utilize the second kinematics equation. That was bad to me. So this is not initial velocity. This is, I was testing you guys. This is actually final velocity, right? So this is final velocity because this is the vertical velocity right before it hits the floor. We actually know VO to be 0. And that's completely, or the vertical initial velocity to be 0. And it's completely not my fault. Definitely not my fault. Okay, so this problem actually becomes a lot easier than expected. I can just utilize the first equation. So we have the final velocity to be, so I'm going to utilize this. Okay, so we have the final velocity to be 2GH1, and then we have VO to be 0, and then plus acceleration is G, right? And then we're looking for time. Then I just divide by G, and I get the square root of 2GH1 over G is equal to time. Okay, this problem's a lot easier than I expected, and that is, that's my bad. So we're going to plug in this time to this equation. VH is equal to distance over time. VH is the square root of 2GH2 is equal to, and then the time we have now is square root of 2GH1 over G, and then we're just going to multiply. Okay, so when we multiply this, 2GH1, and then so we're going to see what here, 2GH2. So what I'm going to do here is I'm just going to multiply. Okay, so we're going to have the square root of 2GH2 times, right, 2G sorry. Um, so yeah, times the square root of 2gh1 and over g, and that's going to be the distance. Okay, I'm sure we can simplify it some more, but that's the basics of it. So that's going to be distance for this problem. Oops. Okay, so now we can look at E. So E is going to be a lot easier. E is qualitatively describe what happens to the energy, the velocity, and the final landing position of the box if the box is given an initial push down the ramp. So what they're saying is that, like, hey, we're not just going to release this box, right? It's not going to have just potential energy because we're giving it a push. So that means in the beginning, we won't just have the potential energy, we're also going to have some kinetic energy. So that means we will have more energy for the system. That's basically what it means. If we're pushing it down, it's going to have an extra kinetic energy. And so that means if it has more energy, okay, if it has more energy, that means we have more to work with, right? If we so that means so what happens here is that since we will have more energy, this vertical velocity will be higher. And if the vertical velocity will be higher, that means if the vertical velocity is higher, that means, right, it will travel more distance, right? It will travel more horizontal distance. If it travels more horizontal distance, it's going to travel, right, at a further x. So the landing position of x will be further than it was before, right? The energy will increase because we're adding more energy into the system. Again, it just doesn't start off with potential energy. Since we're pushing it down, it will start off with potential and some kinetic energy, so it will have more energy to begin with, right? So the amount of energy that we're going to have in the system is going to be higher. And the velocity of the system, right? The velocity will also be higher because, like, we're adding more, or we have more energy. If we have more energy to work with, we have more energy to turn into kinetic energy. Okay, that's basically what it is. So let's look at number 2, or the second problem that we're going to work with. The second problem we're going to work with is it's going to be a spring problem. Okay, so important things to know about a spring: the force of a spring is going to be kx, right? The potential energy of a spring when it's compressed or when it's stretched is going to be 1/2 kx. Right, those are the important things to know about springs. We know k is a constant, right? It's a constant typically given to us, and x is going to be the distance compressed or the distance stretched. Okay, so here we have a toy of mass m is held at rest against a compressed spring with a spring constant k and compressed at distance d. The car leaves with the spring with an unknown velocity. Qualitatively describe the potential energy and kinetic energy of the car when it is held at rest and then released. Okay, so pretty simple. Okay, so we're gonna have like a spring, right? And there's going to be like a car attached to it. And what happens is it's going to be compressed, and we're going to release it, right? So it's going to be released, and it's going to travel to the right. Okay, so the basics here is we're going to qualitatively, meaning like without numbers, okay, describe the potential energy and kinetic energy of the car when it is at rest and then released. So we know, right, when the car is compressed or when the spring is compressed, we know it's going to have potential energy, right? The potential energy it's going to have is going to be elastic potential energy. So the energy it has when it's fully compressed, right when it's at rest before we release it, is going to be just potential energy or elastic potential energy. Okay, and then when we let it go, that elastic potential energy turns into kinetic energy. So that's basically what you're going to do, right? You're going to say while the spring is compressed, all of the energy becomes, or fully compressed, all of the energy is elastic potential energy, right? When it's released, that elastic potential energy is slowly turning into kinetic energy, right? Until we hit equilibrium. When we hit equilibrium, right? When the spring is neither stretched nor compressed, when we hit equilibrium, then the car will only have kinetic energy. Okay? That's basically what we're going to say. It's going to have potential energy at the beginning while it's compressed. Then when you let it go, that energy is going to slowly turn into kinetic energy. And once the spring is at equilibrium, all of that energy that it started off with becomes kinetic energy. And so now we're going to look at part B. That's part A. So part B is derive an expression for the velocity of the car once it's at equilibrium position. Okay? Again, the total energy of the system when it's compressed, right, it's just going to be elastic potential energy, US, right? So that potential energy at the beginning, while it's compressed, is going to be 1/2 kx squared. And they tell us that the k is just k, and x is going to be d, okay? So instead of x, I'm going to put d squared. So that's the total energy that it has at the beginning, because total energy was just elastic potential energy, okay? But then we know at equilibrium, so this is at compressed, and total energy at equilibrium, right, is going to be just kinetic energy. So that's just going to be 1/2 mv squared. We know the mass is m, we don't know v, and that's what we're looking for. Okay, so we're looking for v, and it's very important to understand, because of the conservation of energy, that the total energy when it's compressed and the total energy at equilibrium is going to be exactly the same. That means we can make these two equations equal to each other. So I'm going to have 1/2 kd squared is equal to 1/2 mv squared, right? And we're going to solve for v. Again, super simple. So I'm going to multiply the 1/2. Kd squared is equal to mv squared. Then divide by m. So kd squared over m is equal to v squared, and v is equal to the square root of kd squared over m. That's the basics of it, right? So that's going to be the velocity, right, or expression for the velocity when it is when you release it, right, when it reaches equilibrium, because all of this energy, all of the potential energy, becomes kinetic energy. So let's look at part C. Part C is consider the spring constant to be, put here, the spring constant to be 250 newtons per meter. Compressed distance, so the d is, so x is going to be 0.9, right, because this is 90 centimeters, we have to convert it to meters, 0.9 meters, and then the mass is 3 kilograms, okay? And then the velocity when it reaches equilibrium, okay, velocity at equilibrium is going to be 4 meters per second, okay? And the question is, did an external frictional force act on the toy car during the release? If not, why not? If so, what was the value of this force? So what we can do is, hey, I know that when it's compressed, it's only going to have potential energy. So let's calculate how much energy it's supposed to have before you release it. So when it's fully compressed, you know it's only going to have 1/2 kx squared or 1/2 kd squared. So we can easily solve for that. So the total energy when it's compressed, right, again, is going to be potential energy, right, or elastic potential energy. And we can solve for that. We know that it's going to be 1/2 kx squared, so 1/2 k is 250, okay, and then the x is going to be 0.9 squared. So the amount of energy it's going to have is whatever this is, and I don't know, so let's get a calculator. So we have 125 times 0.81, I believe, and that's going to be 101.25 joules. So that's how much energy the system has, right? So when we know when it was fully compressed, it only had potential energy, and the amount of potential energy it has is this. So that's how much energy the system has, and that's how much energy we have to work with. And then let's look at for the total energy at equilibrium. We know the total energy at equilibrium will just be kinetic energy, because it's no longer a compressed or stretched, so we know it's only going to have kinetic energy. Okay, and we know the velocity it's going to have, so it's going to have 1/2 m is 3. Okay, velocity is 4 squared, so 4 squared is 16 times 3 is 48, divided by 2, 48 divided by 2 is 24. Okay, so if you notice here, like, hey, okay, this is different. So remember, right, the energy is supposed to be conserved. The energy we have in the beginning and the energy we have at equilibrium is supposed to be exactly the same, and in this case it wasn't, right? So that means some energy was lost. In this case, the energy was lost due to frictional force, right? So we know that energy is lost, and the question is, right, so we know that the frictional force took away some energy, and you say, yes, it took away some energy because the energy it had compressed and the energy it had at equilibrium are different, right? Since they're different, we know that the friction took away some force. But the question is also asking, what is the value of this force? Okay, how much work right? Or how much force did friction do to be able to do this, right? To be able to take away this force, right? And if we calculate 101.25 minus 24, we know that the work done by friction is going to be 77.25 joules, right? Because it took away that much force. And we know work is force times distance. We know the distance to be 0.9, right? So we can easily solve for it. So we know the work is 77.25. We know the distance is 0.9, so we can easily solve for it. So we know the force, right? The force friction, the amount of force friction applied was 85.833, right? Units. Okay. 33 units. Okay, so that's how much force friction applied. Pretty simple. So let's look at part D. I know I wrote on it, but whatever. Assume that this part of the spring, assume for this part the spring constant is unknown. If you are given a meter stick and an electronic force sensor, describe the procedure for determining the spring's constant of the spring. You do not have the equipment needed to measure the velocity of the car after release. So basically what they're telling us here for part D, we don't know, okay. And what we do have is a meter stick. And we have an electronic force sensor. Okay, so basically what they're telling us here, we can easily find out the value of x, we can find the value of the distance, right? And we can find, or the distance compressed or the distance stretch, and we can find out the force, right? We can find out how much force is applied for this distance, how much force is applied for this distance, right? That's what they're telling us. So we can find these using the equipments that we have, but those are the only things that we can find, okay? And we're supposed to find k. Again, super easy. Force is equal to kx, right? Super easy. If I know the force, okay, I know the x because of the meter stick. To find it, I just do force divided by x gives me k. Again, super simple stuff. And that's it. So we're going to do one more problem, and this is going to be another roller coaster problem, but it mostly deals with the concept of energy. So here we have a 0.1 kilogram block is released from rest at point A, as shown above, a vertical distance of h above that ground. It slides down an inclined track around a circular loop of radius 0.5 meter, and then up another incline that forms an angle of 30 degrees with a horizontal. The block slides off the track with a speed of 4 meters per second in point C, which is at a height 0.5 meters above the ground. The entire track is said to be frictionless and air resistance is negligible. Okay, so again, we have a system, right? We have a block that is at rest. So that means if it is at rest, it's not moving. That means it has no kinetic energy. That means the system, right, over at point A, the total energy at point A is just going to be potential energy. Okay, and then let's look at point B. It's going to slide down in a frictionless track. It's going to go around, and it's going to reach this point, right? And it's going to have a velocity at this point because it has to go up this up the loop, so it's going to have a velocity at that point. But since it has a height, we know it has potential energy. So at this point, total energy at point B is going to have kinetic energy because it's moving, and it's also going to have potential energy. Okay, same thing for part C. Part C is going to have a velocity of 4 meters per second according to this problem. Okay, so it's going to have, and it has a height, so we know it has potential energy. So the total energy for part C, or for point C, will be both kinetic and potential. And it's also important to note that the total energy, right, since there's no friction, the total energy for point A, point B, and point C are going to be all the same because of the conservation of energy, right? Or the law of conservation of energy. So part A is saying, hey, determine this height. Determine the height h. Okay. So let's think about what we know, right? So we know at point A, right, that's what we're typically working with height h, right? Because we know the potential energy, and I'm going to draw A here, or I'm going to put A. The potential energy that it has at the beginning is going to be due to the height h. Okay, so we know TA point A is just potential energy, and potential energy is mass times gravity times height. So that's m times g times h. We know the mass of the object is 0.1. Okay, so I can put 0.1, and then gravity is gravity, so that's still g or 10. Okay, I guess we can put 10, and then we looking for the height. Okay, so we're looking for the height, but that's all we know. But we know, hey, it's like, hey, right, I can't really solve for this problem yet. I can't really find h just with looking at point A, but I know that the total energy of point A and point B and point C are all the same. Okay, and I know I'm trying to look for, like, hey, which one do I know more of? Do I know more of point B, or do I know more of point C? Okay, so point B, all we know is the height. All I know is the height is 0.5. Okay, because that's the radius of the circle. That's all I know. I don't know the velocity at point B. All I know is the height. But at point C is, hey, I know the velocity, and I also know the height. Since I know about point C, let's try to work with it, right? So let's try to work with point C. So again, the total energy at point C, right, is going to be a mixture of kinetic and potential. Yeah. So I know the kinetic is 1/2 mv squared. 1/2. The mass of the object is 0.1. Okay. The velocity at point C is going to be 4 meters per second, so that's 4 squared. And I know, and I can find potential energy. Mass is 0.1, g is 10, and then we know the height, right? The height is going to be 0.5. It's like, hey, I can solve for C, right? I can find the total energy at C. So if I do this problem, let me just solve for it. This is this is 16. 1.6. This is 8, I think. Yeah, this is 0.8 plus this is 1 plus 0.5. Okay, so this is really weird, but the potential energy. Okay, so what we have here is now we can find the total energy at point C. The total energy of point C is 1.3 joules. Okay, so that's going to be the total energy for point C. And we know the total energy for point C is the same as total energy for point A. So that means this equation for potential energy is equal to 1.3. So I can easily solve for that. So I have 1 or 0.1 times 10 times h, okay, is equal to 1.3 joules. Okay, so if I solve for this is 0.13, 0.013 is equal to h. Okay, if you do the mathematics calculation. So part A is like, hey, the height is 0.013 meters. Okay, it's very, very small. That's it. So that's part A. Part B is saying, on the figure below, draw and label all the forces acting on the block when it is a point B. So looking at point B, what forces are acting on it, right? So if we draw a free body diagram, and we know that it's going to have, like, it's going to be, if this is a circle, right, it's going to be at this side. So we know it's, leaning against the surface. It's like, hey, if I know it's against the surface, I know there's going to be normal force, right? And I know there's going to be gravity. Okay, so I can write that down. I know there's going to be a horizontal normal force, and there's going to be gravity. And that should be it, right? There's no friction. If there was friction, it will also be pointing down, but there's no friction. So this is going to be the forces acting on this object. So part C, determine the magnitude of the velocity when it is a point B. So we're going to find the velocity at point B. Again, this is super easy. We know the total energy, the equation that we're going to use for the total energy of B. It's a mixture of kinetic and potential. Okay, so we're looking for part C, right? So we know total energy at point B is going to be kinetic and potential. And I know, right? I don't know kinetic, or I don't know the velocity, but I know it's mass, right? But I don't know the speed. I know potential. I know it's 0.5 meters away from the ground. So mass is 0.1, g is 10, and then height is 0.5. So easily, I can solve for V. Okay? Because I know the total energy of the system, we solved for it here, the total energy of the system is going to be 1.3 joules. Because remember, the total energy of the system at C, at B, A are all the same. So I can solve for this. This is 1.3 is equal to 1/2 0.1 V squared plus 0.1 times 10 times 0.5. Right? I'm just going to solve for V. So let's try to figure that out. Okay. Oops. So this becomes when. So if I solve for this, this will be like 0.05 v squared plus 1 times 0.5, which is 0.5, is equal to 1.3. Okay, then I supply 0.5, that's 0.8 is equal to 0.05 v squared, right? And then I divide by 0.05, so 0.8 divided by 0.05 is going to be 16 is equal to v squared, and then the square root of 16 is 4. Okay, so the velocity at point B is going to be 4 meters per second. That's it. Okay, so this is 4 meters per second. Yeah. And then now let's look for part D. Part D is determine the magnitude of the force exerted by the track on the block when it is a point B. So force that's being exerted on the by the track on the block is normal force, right? So that's the force that's being applied here. And this is where we're going back to circular motion. So we know that the linear velocity of the track, right, during this like loop at point B is going to be 4 meters per second. So I know the velocity during this time, right? So let me put, I guess I'm gonna go here. So let's look at part D. So I know the velocity is 4 meters per second, okay? And I know the normal for the force that we're looking for, normal force. And remember, and if you load this here, right, this normal force is towards the center of the circle. Remember, the force that's towards the center of the circle is going to be your centripetal force, right? It's the only force that's, you know, in the same axis as those that are pointing towards the circle. So that means that this Fn is going to be your circular motion, or your sum of your centripetal force. And remember, centripetal force is mv squared over r. That means Fn is equal to mv squared over r. It's like, hey, okay, so I know m is 0.1, I know v, I just solved for it, is 4, and I know r, the radius of the track, or the radius of the circle, is 0.5. Okay, so now I can easily solve for it. And Fn is equal to, this is 4 squared is 16, times 0.1 is 1.6, this is times 2, it's going to be 3.2 newtons. Okay, so force that the track is applying will be 3.2 newtons. Okay, basically E is determine the maximum height above the ground attained by the block after it leaves the track. Okay, so we know it's going to leave a track at 4 meters per second, right? So we know the block is going to leave the track at 4 meters per second, but this is very important. It's going to leave the track at 4 meters per second, okay? But we also know, and this is super, super important, but we also know that this is a velocity at an angle. Okay, so if we're looking for the maximum height, then we're not looking for things at an angle. We're only looking for the vertical part. So we would have to find the vertical component of this velocity. Luckily for us, we have an angle. We have an angle of 30 degrees. So we know the vertical component, right, is going to be the sine component. So all I have to do is 4 times sine of 30. Okay, let me figure that out. 4 times sine of 30, make sure calculate is in degrees, and that's going to be 2. So that means the vertical velocity will be 2 meters per second. So if I know so now I'm looking for the maximum height, and again, this is not going to be hard. So this is part E. Okay, so if I know the vertical velocity, then that's going to be the initial velocity, is going to be 2 meters per second. And I know if I'm going to reach the maximum height, I know at the maximum height, it should have a velocity of 0 meters per second. And I know gravity, right? So we have acceleration due to gravity is negative 10 meters per second, right? Or g. Yeah, and then I'm looking for the change of x. At this time, I'm looking for the distance traveled vertically, right? So I would just have to use kinematics, right? I can use the third equation. So I'm going to have vf squared is equal to v squared plus 2a change of x. So this is going to be 0 squared is equal to 2 squared plus 2 times negative 10 times change of x. Okay, so if I'm going to solve for this, it's going to be negative 4 plus equals to negative 20 change of x. So I'm going to divide. Negative 4 divided by negative 20 would be 0.2, I believe. Yeah, it would be 0.2 is equal to change of x. So that means the distance, the maximum distance that it's going to travel up will be 0.2 meters, right? But the thing is, it already is at 0.5, so it's going to travel 0.2 higher. So it's going to travel a total, like at least like horizontally, it will be, or sorry, vertically, it will have a height of 0.7, right? So we have to add those two together. So this would be 0.7. Okay. The last question is another track has the same configuration, but it is not frictionless, right? So there's going to be friction. With this track, it is found that if the block is to reach point C with a speed of 4 meters per second, the height must be 2 meters. Determine the work done by the frictional force. So we're going to look, it's an identical track, but there's a friction, right? But what I can do there is, since I know age already, the first height, right? If I know this height is 2 meters, then I can easily solve for the amount of energy it has to begin with, right? So the amount of energy it will have to begin with. So in this point, this is for part F. Okay, dTEA. Okay, it's going to be, again, it's just going to be potential energy. It's going to be the mass, the same mass, 0.1. Gravity is gravity, so it's 10. And then the height, right, in this case will be 2. So I can easily solve for that. That's going to be 2 joules. So the amount of energy that we have to work with at the beginning is 2 joules, right? But they tell us, like, hey, the block will still leave point C at 4 meters per second. This will still happen, right? It will leave the block at 4 meters per second. So let's look at TEC, or the total energy at point C. Again, total energy is supposed to be the same, but since there's friction now, it's not going to be the same, because some energy will be lost due to friction. Okay? So we know that at C, it's going to have both kinetic and potential energy. Okay? So the kinetic energy is 1/2 mv squared, so 1/2 m 0.1. V is still going to be 4. Okay? And then the height is still going to be the same, right? So there's going to be mass, which is 0.1. Gravity is going to be 10, and then the height will be 0.5. Okay, that's the height at point C, 0.5 meters. So if I solve for this, I'm going to get this is 4 squared 16, 1.6.8 plus 1.5. So this will be 1.3 joules. So if you notice here, right, some energy is lost, right? An easy calculation, the amount of energy lost will be 0.7 joules, right? So that means friction is going to take away 0.7 joules. It's going to work against the motion, right? And it's going to do work against the motion, and it's going to take away 0.7 joules of energy. Okay? And that's it. That's the work done by friction, 0.7 joules of energy. Really, really easy stuff. Okay? And that's this problem. Okay? And that's all I have for you guys. So we're done for today. Ooh, in time. Okay, so we're done for today. Thank you guys for attending. Again, if you have any questions, please email me. If I don't answer, I probably just like get an email, then I get another one, and then things get really confusing. But again, if you have any questions, please ask. Right. Back next week, please, guys. Like those who haven't done the survey, please answer that survey. It's super duper important that you do so like immediately, just so I can especially the ones about like the questions about the devices, right? Like if you guys need a device, if you guys don't need a device, if you need a hotspot, we'll try to like our best to provide that for you for the exam. Super duper important. I don't know. I mean, I don't know. Depends on you guys. Like I'm pretty sure I still have it up. But yeah. So I know the exam will be May 14th. We'll try to do a little bit more problems there. Right beforehand, we'll try to do more things. But it's not a long time, right? Some of you guys have other exams, so we would have like a week or 2 weeks. You want to beat the Ender Dragon? Like, have you guys like built anything? Yeah, I want a thriving city when I come back, guys. I want a thriving city when I come back. When like, so you just like email me your username or like message me your username, and then I'll whitelist you. I want to. Yeah, it's Java though, so it's not like it's not the Bedrock edition. Because these guys told me to utilize Java. Oops.